What if I told you that the most famous equation in history, like the one you probably memorized in middle school, the one we use to explain how the entire physical world actually moves is, well, mathematically incomplete?
Or at least it's a bit of a mathematical mirage that's hiding a pretty massive, dangerous trap.
Right. I'm talking about Isaac Newton here. I'm talking about F equals ma, force equals mass times acceleration. We all learned it. We treat it like absolute gospel. But looking at the massive stack of foundational research we're diving into today, it turns out that treating F equals ma as the fundamental law of physics is, well, a brilliant way to crash a rocket straight into the ocean.
Yeah, it really is the ultimate example of a cognitive trap. It
Mhm.
stems from this deep human desire for oversimplification. We get so eager to find a clean, elegant formula that we just completely forget to read the fine print that allows that formula to even exist in the first place.
It,
And that trap, it doesn't just apply to middle school physics. You see the exact same pattern of misunderstanding everywhere. Like when an aerospace engineer models a control system, or when a computer scientist analyzes an algorithm, or, I mean, even when an economist designs a high-stakes billion-dollar auction.
and so that is our mission for you, the listener, in today's deep dive. Because we rely on these models, these incredibly beautiful, sweeping algorithms and theorems to basically run the modern world. They're the scaffolding of our infrastructure, our economy, our software.
Right, but they are constantly misused.
Constantly,
The-
because people strip away the context.
yeah,
So today, we are extracting the hidden assumptions. We are hunting for what we like to call the guardrails of reality. These are those invisible boundaries that keep theory from just catastrophically failing when it hits the messy, unpredictable real world.
the overarching theme in all of these sources, and we're spanning classical mechanics, linear algebra, complexity theory, mechanism design, all of it, is that a formula is really only a shadow of the truth.
A shadow, yeah.
The guardrails are the actual physical or mathematical boundaries that cast that shadow. So if you step outside those boundaries, the formula doesn't just become slightly inaccurate, it becomes actively destructive.
Okay, let's unpack this, and I want to jump straight into the deep end with Newton. F equals ma. Because if that is just a shadow, what is the actual fundamental law that's casting it? Reading through our physics sources, the general consensus seems to be that blindly applying force equals mass times acceleration to complex systems is just a rookie mistake.
It is. And to understand why, we have to look at how Newton's second law is fundamentally formulated. The true general form of the law states that the external force applied to a system equals the rate of change of its momentum over time.
Okay.
So in the language of calculus, the external force, F, equals the derivative of momentum with respect to time, or dp over dt.
Right, okay, so drawing on my high school physics here, momentum, which is p, is just mass times velocity, right? Like an object's weight multiplied by how fast it's going. So if force is the change in momentum over time, you are basically taking the derivative of mass times velocity.
Precisely. And this is where the math demands a really strict guardrail. If you remember the product rule from calculus,
Oh boy, vaguely.
well, taking the derivative of two things multiplied together. So mass and velocity means you get two separate terms. First, you get mass times the change in velocity, which gives us our familiar mass times acceleration.
Okay, there's the ma.
Right. But you also have to add the second term, which is the velocity times the change in mass.
Ah, okay. So the only mathematical way you end up with the clean, simple F equals ma is if that second term just entirely vanishes, meaning the change in mass has to be exactly zero.
Exactly. That is the first massive guardrail. F equals ma assumes you are dealing with a system whose mass is perfectly statically constant. If you're, I don't know, pushing a block of wood across a table, your mass isn't changing, so F equals ma works beautifully.
Right.
But what happens if you apply that stripped-down formula to a system that is actively losing or gaining mass?
Well, you would completely fail to account for the energy tied up in the mass that's actually leaving the system, which immediately brings to mind early rocketry. A rocket isn't a solid block of wood. I mean, it's essentially a giant flying fuel tank that is violently expelling its own mass out the back as exhaust.
A rocket is the textbook example of a variable mass system. When it launches, it burns through thousands of pounds of fuel every single second, so its mass is dropping rapidly.
Yeah.
If you try to model the thrust and trajectory of that rocket using just F equals ma, your physics engine will completely collapse.
Because it thinks the rocket still weighs what it did on the launch pad.
Basically, yeah, you have to account for the momentum flex, which is the momentum being physically carried away by the exhaust plume. You must track the velocity of the expelled mass relative to the rocket itself, and that gives you the Tsiolkovsky rocket equation. If you ignore that foundational dp over dt and just try to plug a changing mass into F equals ma, you literally violate the conservation of momentum.
And your rocket trajectory is going to be off by hundreds of miles.
Exactly.
That is just incredible. We strip away the complexity so it fits neatly in a textbook, and in doing so, we delete the exact mechanism that gets us to orbit. But our sources point out a second, equally critical guardrail for Newton's laws. You need a constant mass, sure, but you also need a strictly inertial frame of reference.
Yes, this is huge. Newton's laws only take their standard expected form if you are measuring them from a vantage point that is not accelerating and not rotating, an inertial frame.
Right.
The moment your perspective starts spinning or speeding up, the classical equations just appear to break.
I really want to visualize this, because frame of reference can be such a slippery concept. So imagine I'm sitting in the passenger seat of a car, and the driver takes a really sharp left turn at a high speed.
Okay, picture that.
From my perspective, sitting inside that car, I feel a very real physical force slamming me outwardly against the passenger door. We colloquially call it centrifugal force, right? But according to these papers on mechanics, that force doesn't actually exist. It's entirely fictitious.
It is not a real physical interaction force.
Oh.
You have to carefully separate what you feel from what is mathematically occurring. When the car takes a sharp left, the car becomes a rotating, non-inertial frame of reference.
But the bruise on my shoulder from hitting the door is definitely real. How can the force be fictitious?
Well, the force the door exerts on your shoulder is absolutely real. That's a contact force, a normal force pushing inward toward the center of the turn, physically forcing your body to change direction along with the car.
Right, the door is pushing me.
But the supposed outward force that you feel throwing you into the door, that is fictitious. What you are actually experiencing is simply your own inertia.
My body's stubborn desire to just keep moving in a straight line.
Exactly. Before the turn, you were traveling in a straight line. When the driver turns the wheel, your body wants to continue on that exact same straight path. But the car is suddenly curving into your path, so you aren't being thrown outward into the door. The door is turning inward into you.
Oh, wow. So if I'm standing on the sidewalk watching this happen, which is an inertial frame, I just see a car turning into a passenger who is trying to go straight. There's no mysterious outward force at all.
None. But if you insist on doing your physics calculations from the perspective of the passenger seat, which is a rotating frame, the math has a massive problem.
Because I see myself accelerating toward the door, but there's nothing pushing me.
Right. So to make Newton's equations balance in this weird rotating environment, mathematicians have to introduce what we call fictitious or inertial forces. These include the centrifugal force pushing you outward, the Coriolis force, which curves moving objects in a rotating frame, and the Euler force, which appears when the rotation speed itself changes.
It's essentially a mathematical patch. Like the math invents a ghost force just to balance the books, purely because we decided to measure the world from a spinning platform instead of a stable one.
And if you don't explicitly account for the fact that your coordinate system is rotating, your free body diagrams will be fundamentally flawed. You actually see this in meteorology all the time.
Oh, like with hurricanes.
Yeah, hurricane systems spin the way they do because the Earth is a giant rotating frame. Air wants to move in a straight line from high pressure to low pressure, but because the Earth rotates underneath it, the air appears to curve. That curve is the Coriolis effect. It's a kinematic requirement of the rotating frame. It's not a giant invisible hand physically pushing the wind.
Okay, so the classical laws of motion demand a stable stage and constant actors. If we move from mechanics over to electromagnetism, the sources reveal a very similar theme of classical intuition completely missing the underlying reality. Let's talk about electric and magnetic fields. Because the everyday intuition is that if I rub a balloon on my hair and build up a static charge, I've created an electric field. Charges create fields.
That intuition comes directly from Gauss's law, which states that the electric flux outward from a closed surface is proportional to the electric charge enclosed within it. And for static situations, that is perfectly true. But it is really only half the story.
Right, because if we rely solely on Gauss, we assume that where there is no physical charge, there can be no electric field. But the sources highlight Faraday's law of induction, which completely shatters that assumption.
It really does. Faraday's law introduces an entirely different, highly dynamic mechanism for creating an electric field. It states that a changing magnetic field will induce an electric field, regardless of whether there are any physical charges present in the area at all.
So I could be in a perfect, pristine vacuum in deep space, not a single electron for light years. But if I have a fluctuating magnetic field, an electric field just spontaneously curves into existence out of nowhere.
Mathematically, yes. The curl of the electric field equals the negative rate of change of the magnetic field.
Mhm.
They are intimately coupled. I mean, this is the absolute bedrock of our entire electrical grid.
Wait, how so?
Well, a generator at a power plant doesn't work by harvesting static charges. It works by physically spinning giant magnets. That changing magnetic field induces an electric field in the surrounding copper coils, which then drives the electrons to create current. If you take the formulas you learned for electrostatics, which assume a static, unchanging universe, and try to apply them to a time-varying environment, you will be completely blind to induced fields.
The guardrail is time. If things are changing over time, the static rules just go right out the window.
But speaking of magnetic fields, there's a paradox in these electromagnetism papers that initially broke my brain.
Oh, I think I know which one you mean. Yeah, we use giant electromagnets in junkyards to pick up incredibly heavy crushed cars. The magnet clearly lifts the car against gravity, but the physics sources state, unequivocally, that magnetic forces do zero instantaneous mechanical work on a point charge. How on earth can a force that lifts a 2-ton car do zero work?
It is such a brilliant paradox because it forces you to reconcile macroscopic observation with microscopic mathematical reality. To understand why the magnetic force does zero work, we have to look at the Lorentz force equation for a single moving point charge.
Okay, lay out the mechanism for me.
The magnetic component of the Lorentz force is calculated using a cross product. The force vector is proportional to the charge, multiplied by the cross product of the particle's velocity vector and the magnetic field vector. Now, in linear algebra, a cross product of two vectors always results in a third vector that is perfectly perpendicular or orthogonal to both of the original vectors.
So if my particle is flying straight forward and the magnetic field is pointing straight up, the cross product dictates that the magnetic force pushes perfectly sideways.
Exactly. The magnetic force is, by definition, always exactly perpendicular to the direction the particle is actually moving at any given instant. Now think about how work is defined in physics.
It's the transfer of energy, right?
Yes, mathematically, it is the dot product of the force vector and the velocity vector. It measures how much of the force is pushing directly along the path of motion.
And if the force is pushing perfectly sideways, like 90 degrees away from the motion, the dot product is just zero.
Precisely. A perpendicular force cannot speed a particle up, and it cannot slow it down. It can only change its direction. It steers the particle into a curve, but it transfers zero kinetic energy. Therefore, the magnetic field itself does absolutely zero instantaneous mechanical work on that charge.
Okay, so we're back to the junkyard. The magnet is steering the electrons fine, but the car goes up, something is fighting gravity and winning. If the magnetic field isn't doing the work, what is?
Well, when you scale up from a single point charge to a massive piece of metal like a car, you are dealing with a complex lattice of atoms and electrons. The changing magnetic field from the crane induces electric fields within the metal of the car. The magnetic field also interacts with the intrinsic magnetic moments of the atoms, forcing them into alignment.
So it's like a scaffold.
Exactly. The magnetic field acts as the crucial intermediary. It connects the crane to the car. But the actual mechanical work, the force displacing the mass upward against gravity, is being done by the induced electric fields and the internal electrostatic forces holding the metallic lattice of the car together as it gets pulled.
That is such a profound distinction. The magnetic field is just the steering wheel, but the electric fields are the engine actually doing the lifting. It's a perfect example of how a macroscopic assumption completely misinterprets the microscopic mechanism.
And we see that same tension between the macro and the micro when we look at electromagnetic waves themselves, like light or radio waves. I mean, the universal assumption, the one everyone knows, is that the speed of light is a constant, usually denoted by c, which is roughly 300 million meters per second.
Right. Nothing goes faster than light. It's the universal speed limit.
It is a constant, yes, but only in a perfect vacuum. The guardrail here is the medium of propagation. Our sources emphasize that when an electromagnetic wave travels through a real physical material, like a fiber optic cable or a pool of water, or even just the Earth's atmosphere, it interacts with the atoms in that material. Real materials are dispersive. They have electric permittivity and magnetic permeability.
Which means the material responds to the wave, absorbing and re-emitting the energy, and that causes the wave to slow down.
Well, it is much more complex than simply slowing down, and this is where telecommunications engineers have to be incredibly careful. In a dispersive material, a wave pulse actually fractures into two different velocities. You have the phase velocity and the group velocity.
Okay, I need an analogy for this because an electromagnetic wave fracturing sounds a bit abstract.
Sure. Think of a wave pulse as a marching band walking down a street.
Okay, got a marching band in my head.
The overall shape of the marching band, like the rectangular block they form, is the group. The individual members moving their legs inside the block represent the phase. Now, in a vacuum, the individuals walk at the exact same speed that the rectangular block moves forward. So phase velocity equals group velocity.
But in a dispersive material.
In a dispersive medium, the individuals, the phase, might actually be walking faster than the overall rectangular block is moving. As they reach the front of the block, they sort of fade out, and new members appear at the back.
Oh, weird.
Yeah, the phase velocity, which is the speed at which the individual peaks of the wave move, can be completely different from the group velocity, which is the speed at which the actual envelope of the wave, and therefore the energy and the information, travels.
So if I'm designing a fiber optic network for high-speed internet, and I need to know exactly when a data packet will arrive, I can't just use the speed of light, and I can't even just use the phase velocity. The information is strictly carried in the group velocity.
Exactly. If you just assume everything travels at c, or if you conflate phase and group velocity in a dispersive medium, your timing protocols will fail catastrophically. The wave will arrive out of sync, the data will smear into static, and the whole system collapses.
Man, so we've established that physical laws demand pristine environments, vacuums, constant masses, unaccelerated frames to act the way we expect them to. But to even describe those vacuums and masses, we have to use the language of mathematics. And as we transition into the math here, it becomes clear that these mathematical shortcuts introduce a whole new set of traps. I want to look at linear algebra next, because this is the bedrock of modern computing, machine learning, simulations, all of it.
Linear algebra is entirely about solving systems of equations at scale. And the most fundamental operation is solving for unknown variables, which is written as the matrix equation x equals b. Right? Matrix A contains your coefficients, x is the vector of variables you want to find, and b is the output.
Now, if this were standard algebra, like 5 times x equals 10, I just divide both sides by 5. But in linear algebra, you can't technically divide by a matrix, so you find its inverse, you find the inverse of A, multiply it by B, and boom, you have your answer. We spend entire semesters in college calculating matrix inverses by hand. But the computational sources here practically have warning labels on this. They insist that in a numerical, computer-driven setting, you should almost never explicitly calculate the inverse of a matrix.
It is one of the most common and dangerous anti-patterns in scientific computing. From a pure theoretical math standpoint, multiplying by the inverse is perfectly valid. But computers do not do pure math. They do floating point arithmetic, which is inherently inexact.
Because a computer has limited memory, it has to round off decimals eventually.
Precisely. And calculating the explicit inverse of a matrix requires an immense number of operations. It scales cubically with the size of the matrix. Yeah. And every single operation introduces a tiny rounding error. If your matrix is what we call ill-conditioned, meaning its outputs are highly sensitive to tiny changes in its inputs, the process of inverting it will act like an amplifier for those rounding errors. By the time the computer finishes finding the inverse, the microscopic decimal errors will have compounded so massively that your final matrix is essentially numerical garbage.
So the mechanism of inversion itself destroys the precision. So if we can't invert, how do we solve the system without crashing the simulation?
And computational guardrail here is matrix factorization, or decomposition. Instead of trying to find a single, highly unstable inverse, you break the original matrix A down into simpler, more stable parts.
Like breaking a complex mechanical lock down into its individual pins and springs so you can manipulate them one by one.
That is a really brilliant way to conceptualize it, yeah. You simplify the geometry. LU factorization breaks the matrix into a lower triangular and an upper triangular matrix. Because they are triangular, you can solve the equations through simple forward and backward substitution, which requires vastly fewer operations and isolates the floating point errors.
That makes a lot of sense.
And if the matrix is symmetric and positive definite, you use Cholesky factorization, which is even faster and more stable. You never form the inverse. You factorize and you substitute.
Okay, but Lu and Cholesky assume the matrix is a nice, perfect square. What if my system is messy? What if I have 10 variables but 100 equations? This happens all the time in data fitting, where you have way more data points than parameters. We're taught to use the more Penrose pseudo-inverse to find the best fit. The standard formula involves taking A transpose, multiplying it by A, inverting that result, and multiplying it by A transpose again.
And that specific formula is a massive, widely abused trap. That formulation of the pseudo-inverse only holds true mathematically if the original matrix A has full column rank.
What does full column rank physically mean for the data, though?
It means every single column in your matrix represents a completely unique, independent piece of information. Geometrically, they point in different dimensions. But real-world data is almost never perfectly independent. You often have redundant sensors or highly correlated variables. If you have redundant columns, your matrix is rank deficient.
And what happens if I run that pseudo-inverse formula on a rank-deficient matrix?
The mechanism breaks completely. When you multiply A transpose by A, the resulting matrix will be singular. Geometrically, a singular matrix means you have collapsed your volume down into a flat plane. You have lost a dimension of information. When your code attempts to invert that singular matrix, it is effectively trying to divide by zero.
Yikes.
Yeah, the algorithm will crash or spit out infinities.
Because it's trying to find a single unique intersection point among planes that are lying perfectly flat on top of each other. It's impossible.
Exactly. The guardrail for rank-deficient matrices is to abandon that formula entirely and use singular value decomposition, or SVD. SVD carefully extracts the underlying structure and filters out the zero dimensions, allowing you to compute a stable pseudo-inverse without dividing by zero.
It is just amazing how much of our basic math assumes a perfectly well-behaved universe. I want to look at another area where linear approximations lie to us: differential equations and dynamical systems. This is the math we use to predict how systems change over time: weather, populations, drone flight controls. The ultimate question in these systems is stability. If I perturb the system, does it calm down or does it explode?
Right, and to determine stability, engineers often linearize the system. They look at the current state, calculate the eigenvalues of the system's matrix, and look at the real part of those complex numbers.
Because if the real part of the eigenvalue is strictly negative, the system is stable. It means the perturbations decay exponentially over time. The drone returns to a level hover.
For a linearized system, yes, a strictly negative real part guarantees stability. But the massive guardrail here involves the edge case. What happens if you linearize the system and you find an eigenvalue where the real part is exactly zero?
My intuition says zero means it's perfectly balanced. It's not decaying, but it's not growing either, so it's stable.
And that intuition is incredibly dangerous. In nonlinear dynamics, if the real part of the eigenvalue is exactly zero, the linearization tells you absolutely nothing. It is a completely inconclusive mathematical dead end.
Wait, why?
Because when you linearize a system, you are intentionally throwing away all the complex, higher-order nonlinear terms, the squared variables, the trig functions. You assume they are too small to matter near the equilibrium point.
Yeah.
But if the linear forces sum to exactly zero, then those microscopic nonlinear terms are suddenly the only forces left driving the system.
Oh, I need a physical analogy for this. It's like trying to balance a pencil perfectly on its tip. If I look at the macro linear forces right at that exact split second, the gravity pulling down and the table pushing up sum to exactly zero, the linear math says it's perfectly balanced. But just because the linear forces are zero doesn't mean it's going to stay there if a microscopic nonlinear breeze hits it.
That is a perfect visualization. Zero eigenvalue just means the pencil isn't actively falling in this microscopic instant. But the nonlinear dynamics, the shape of the tip, the air currents, the tiny vibrations in the floor, will absolutely cause it to fall over eventually. This is why we have to distinguish between different types of stability.
Right, the sources break stability down into different definitions.
There is Lyapunov stability, which essentially means if you start nearby, you stay nearby.
Oh.
Think of a marble sitting at the very bottom of a perfectly flat trough. If you nudge it, it rolls a little bit and stays in the new spot. It doesn't explode away, but it also doesn't return to exactly where it started.
And the other type?
Asymptotic stability. This is much stronger. This means not only do you stay nearby, but you actively converge back to the exact original equilibrium, like a marble rolling in a round bowl. Gravity actively pulls it back to the absolute center. An eigenvalue of zero might mean the system is Lyapunov stable, or it might mean a hidden nonlinear term is going to cause polynomial growth that destroys the system. You simply cannot know without analyzing the nonlinear math that you originally threw away.
So we linearize to make the math easy, but in doing so, we blind ourselves to the very forces that will tip the pencil over.
Wow.
Let's shift from absolute certainty to probability. People love to use statistics to sound authoritative. If they have a large enough data set, they assume the math will magically smooth out all the chaos. Our sources highlight two mathematical pillars that people abuse constantly: the law of large numbers and the central limit theorem.
The central limit theorem, or CLT, is arguably the most misapplied theorem in all of applied science. The general assumption is that if you take enough random, independent observations and average them together, the resulting distribution will always form a beautiful, symmetrical, normal distribution.
The classic bell curve.
Exactly.
And bell curves are comforting. They tell us that extreme outliers are so astronomically rare that we can basically ignore them.
But the CLT is not a universal law of nature. It is a mathematical theorem with massive, rigid guardrails. First, the variables must be independent and identically distributed. But the absolute critical guardrail, the one that arguably caused the 2008 financial crisis, is that the underlying probability distribution must possess a finite mean and a strictly finite variance.
We need to unpack that. What does it physically mean for a data set to not have a finite variance?
Variance measures how spread out the data is. A normal distribution has a finite variance. The probabilities drop off exponentially the further you get from the average. Like an extremely tall person might be 7 feet tall, but you will never, ever meet a person who is 70 feet tall. The variance is constrained by physical reality.
Right.
But in complex systems like financial markets, internet traffic, or earthquake magnitudes, the data follows power laws. These distributions have extremely fat tails.
Meaning the extreme outliers aren't just slightly possible, they are statistically inevitable.
Exactly. In a fat-tailed distribution, a single extreme observation can be so massive that it completely dominates the entire dataset, skewing the mean infinitely. If you try to apply the central limit theorem to a fat-tailed system, assuming that the variance is finite, your model will compress those fat tails into a neat little bell curve. You will mathematically convince yourself that a stock market crash or a catastrophic flood is a 10,000-year event, when in reality, the fat tails dictate it will happen next Tuesday.
This is exactly what happened with the Gaussian-Coppola formula on Wall Street, isn't it? They assumed housing prices followed a bell curve with finite variance. When the fat tail reality of correlated defaults hit, the model said it was impossible, even as the banks were collapsing.
They ignored the mathematical guardrail of finite variance because the bell curve was just easier to compute.
Unbelievable. Speaking of probability traps, there is another one in the sources that completely short-circuited my intuition. The text notes that there is a widespread fundamental misconception that disjoint events are independent. Let me push back on this because based on the English definitions of those words, it doesn't make sense. Disjoint means mutually exclusive, right? They don't overlap.
Correct. Two events are disjoint if they absolutely cannot happen at the exact same time.
Okay, so let's say there are two rooms. Event A is me standing in room A. Event B is me standing in room B. I cannot be in two places at once. Those are mutually exclusive disjunct events. Because they do not overlap in any way, shape, or form, aren't they completely independent of each other?
That is the exact cognitive trap. You are conflating physical separation with statistical independence. In probability, disjoint events are highly, almost perfectly dependent.
How?
You have to look at the strict mathematical definition of independence. Two events are independent if and only if knowing the outcome of event A gives you absolutely zero new information about the probability of event B.
Okay.
Think about your rooms.
Yeah.
Before I know anything, there's a 50% chance you are in room A and a 50% chance you are in room B. But the moment I observe event A, the moment I see you standing in room A, what happens to my knowledge of room B?
Well, I'm not in room B. You know that for a fact.
Exactly.
Yeah.
My knowledge of your presence in room B just went from a 50% probability to an absolute 100% certainty of 0. Just by observing event A, I gain total deterministic knowledge about event B. Because event A heavily influenced the probabilities of event B, they are fundamentally dependent.
Wow, because they are mutually exclusive, knowing one dictates the other.
The only theoretical edge case where disjoint events are independent is if one of the events had a literal 0% probability of ever happening in the first place, which is a totally trivial scenario.
Right.
In the real world, mutually exclusive means intensely dependent.
That completely rewires how I think about statistical overlap. So we've seen how pure math can be incredibly fragile if you ignore the assumptions of variance, independence, or linearity. But these mathematical models don't just live on chalkboards anymore. They are the software running our world. And that brings us to the third phase of our deep dive: calculating reality. The trap of algorithms and computer science.
When you translate pure math into silicon and logic gates, you introduce the rigid physical constraints of time, memory, and binary encoding.
Let's start with the most famous boundary in all of computer science,
Right.
the P versus NP problem. It's the holy grail of computation. If you solve it, you get $1 million prize. The general pop science understanding is that P stands for problems computers can solve quickly, and NP stands for problems that are insanely hard or not polynomial.
And our complexity theory sources are incredibly strict about correcting this. The pop science definition is a fundamental misunderstanding of what NP actually means. NP does not stand for not polynomial, and it does not inherently mean a problem is hard to solve.
Okay, so what is the actual definition of NP?
NP stands for non-deterministic polynomial time. The rigorous definition has nothing to do with how fast you can find an answer from scratch. NP contains decision problems where, if the true answer is yes, there exists a certificate that can be mathematically verified by a deterministic algorithm in polynomial time.
It's about checking the homework, not doing the homework.
Exactly. Sudoku is the perfect analogy. Solving a massive 1,000 by 1,000 grid Sudoku puzzle might be astronomically difficult and might take centuries. But if I hand you a completed grid and claim it's the solution, you can verify if I am right incredibly quickly. You just scan the rows and columns to ensure there are no repeating numbers. Because the verification is fast polynomial time, Sudoku is in NP.
Okay, so NP means fast checking. But what about NP hardness? If a computer scientist proves a routing problem is NP hard, doesn't that just mean no one has been smart enough to find a fast algorithm for it yet?
No, and this is a massive guardrail in algorithmic theory. You absolutely cannot infer that a problem is NP hard just because you haven't found a polynomial time solver for it. Lack of human ingenuity is not a mathematical proof of complexity. To rigorously prove a problem is NP hard, you must perform a very specific mathematical operation called a reduction.
A reduction, meaning translating the logic of one problem into the language of another.
Yes, but the trap is the direction of the reduction. This is where countless papers get rejected. To prove your new unknown problem is NP-hard, you must reduce a known NP-hard problem like the Boolean satisfiability problem to your target problem.
Let me make sure I understand the mechanism here. You have to prove that if I had a magical, hyper-fast solver for my new target problem, I could use that exact same magical solver to quickly decode the known, impossibly hard baseline problem.
Exactly. You are proving that your target problem is at least as complex as the known hard problem because it encompasses its logic. The fatal mistake researchers make is doing it backwards. They reduce their new target problem into the known hard problem.
Which proves what?
It proves absolutely nothing about the underlying difficulty of their target problem. It just proves they found a highly convoluted, overly complex way to solve it. It's like proving you can use a supercomputer to do basic addition. It doesn't mean basic addition requires a supercomputer.
The direction of the arrow is everything. You have to lift the hard problem up to your level, not push your problem down into the hard one. That makes total sense. Now, let's talk about an algorithmic trap that looks fast on paper but hides an explosive reality, a dynamic programming. The sources highlight the famous 0-1 knapsack problem.
The knapsack problem is a foundational optimization challenge. You have a backpack with a strict weight capacity, let's call it W. You have a set of items, N, each with a weight and a value. Your goal is to pack the backpack with the absolute highest total value without exceeding the weight limit.
It's the ultimate heist movie algorithm. What do I steal to get rich without the bag ripping? There is a very famous dynamic programming solution for this that runs in O of NW time, big O notation of N times W. That looks like a simple polynomial equation. If N is 10 items and W is 10 pounds, it takes 100 steps. That looks incredibly fast.
It looks polynomial, but computer scientists classify it as pseudo-polynomial. The big O notation is hiding a massive exponential trap in how computers actually encode and read input data.
This is where the physical reality of the machine clashes with the math.
Precisely. In computational complexity, the size of an input isn't the numeric value of the number. It is the physical number of bits, the zeros and ones it takes to write that number down in computer memory. Let's look at your capacity, W. If your weight capacity is 1 billion pounds, the numeric value is 1 billion. But writing 1 billion in binary only requires about 30 bits of memory.
Okay, so the computer sees an input size of 30.
Right. But your algorithm runs NO of NW time. That means the algorithm has to physically iterate through a loop 1 billion times. The runtime is growing exponentially relative to the tiny 30-bit length of the input.
I need an analogy for this. It is like mapping out a cross-country road trip from New York to LA. But to make your step-by-step instructions look really detailed and impressive, you write them out in inches instead of miles. You're cheating the metric of the input size to make the algorithm look efficient on paper, but when you actually have to drive the route, it takes an eternity.
That is a brilliant analogy. You are inflating the state space. If the capacity W gets even slightly large, the dynamic programming matrix explodes in memory, and the fast polynomial algorithm instantly grinds the computer to a halt. The numeric value of the input cannot be decoupled from its binary encoding length.
That is incredibly sneaky. It looks like a friendly linear equation, but it's an exponential time bomb. Let's look at another area where algorithms fail. Graph theory. Routing data packets over the internet, or GPS navigating a car. The sources mention two heavyweights, Dijkstra's algorithm and the Bellman-Ford algorithm.
Dijkstra's algorithm is a masterpiece of efficiency for finding the shortest path between nodes in a graph. It uses a greedy logic. It assumes that every time it takes a step along a new edge, the total distance of the path must increase or at best stay the same.
Which makes logical sense. If I drive another mile, my odometer goes up. It never goes down.
But that logic is the absolute guardrail. Dijkstra's mathematical proof of correctness collapses the moment your graph introduces negative edge weights.
What does a negative edge weight represent in reality?
It could represent a route that generates revenue instead of costing money, or a battery charging station on a route that gives you negative energy expenditure. If you have a negative weight, a path could actually get mathematically shorter the further you travel along it. Dijkstra's greedy assumption blinds it to this possibility, and it will confidently output the wrong optimal path because it refused to explore a longer route that contained a massive negative payoff at the end.
It's too short-sighted. So if you have negative weights, you have to abandon Dijkstra and use the Bellman-Ford algorithm, which is designed to handle them.
But our sources say people fundamentally misunderstand what Bellman-Ford can actually guarantee.
They do. Bellman-Ford works by systematically relaxing every edge in the graph multiple times, allowing it to correctly tally negative weights. But the massive misconception is that people claim Bellman-Ford can detect every negative cycle in a graph.
A negative cycle being a loop of roads where every time you drive in a circle, you somehow make money. The algorithm would just want to drive in that circle forever, dropping your costs to negative infinity. Exactly. Detecting those infinite loops is critical. But Bellman-Ford only detects negative cycles that are physically reachable from the specific starting node you assigned it.
Like trying to map a time travel anomaly, but the anomaly is on an island with no bridges.
Yes. If there is a negative cycle isolated in some disconnected subnetwork of the graph, your single-source Bellman-Ford run will never send a probe there to explore it. It will finish its run, declare the graph free of negative cycles, and be completely wrong about the global state of the network.
Because it only knows what it can touch. Let's go down to the absolute lowest, microscopic level of computation, the very way machines do arithmetic. We briefly mentioned floating point numbers earlier regarding matrix inversion. I always assume that because computers are literal microscopic calculators, their basic addition is perfectly precise.
And that assumption is the root of some of the most expensive software failures in history. Floating point arithmetic is a finite, binary representation of an infinitely continuous reality. The IEEE 754 standard dictates how computers store decimals, using a set number of bits for the significant digits, the mantissa, and a few bits for the exponent.
Scientific notation for silicon.
Precisely. Because those bits are finite, floating point addition is mathematically non-associative.
Non-associative, meaning the grouping matters. So if I have three numbers, A, B, and C, if I add A and B together first and then add C, the result might not be the same as if I added B and C together first and then added A.
In pure math, they are identical. Numerically, inside the computer's CPU, they can be drastically different. The order in which the machine adds the numbers changes how the microscopic rounding errors are applied and truncated.
That is terrifying.
It gets worse when you run distributed simulations on parallel processors, like predicting weather or fluid dynamics. Different processor threads will finish their calculations and sum their results into the main memory in an unpredictable race condition order. Because floating point is non-associative, you can run the exact same code with the exact same initial conditions and get a mathematically different answer every single time you run it.
And if you happen to subtract two numbers that are very close to each other, you hit a completely different wall.
That is called catastrophic cancellation. Imagine you have two numbers measured to 7 decimal places of precision, 1.000000000, and 1.000000. They are highly precise. But if you subtract them, all those leading precise digits cancel out, leaving you with just the 1 at the very end of the decimal tail.
The precision evaporates instantly.
You lose all your significant digits in a single clock cycle, and you are left calculating the rest of your simulation based entirely on rounding garbage. This isn't theoretical. In 1991, during the Gulf War, a Patriot missile battery failed to intercept an incoming Scud missile. The system tracked time by counting tenths of a second, but the binary representation of 1/10 is a repeating fraction. The tiny floating point truncation error accumulated over 100 hours of the system being powered on.
It drifted out of sync.
It drifted by about 1/3 of a second. Because the Scud was traveling at Mach 5, 1/3 of a second meant the radar gate looked in the wrong place by over half a kilometer. The missile hit a barracks and 28 people died. All because the physical reality of floating point arithmetic was ignored.
So a program can compile perfectly, it can run without a single syntax error, and it can still output scientifically invalid, highly destructive results purely because of the physical constraints of silicon and binary math. That brings us to section 4, designing for the real world. This is where theory and code actually hit the assembly line. Our design methodology sources draw a massive, bright red line between two concepts that corporate jargon uses interchangeably: verification and validation.
They are completely distinct engineering gates, and confusing them is a recipe for building a perfectly functional disaster. Verification asks a purely technical, inward-facing question. Did we build the design correctly according to the mathematical requirements?
So if the spec sheet says the steel beam must withstand 10,000 pounds of shear force, and you put it in a hydraulic press and it holds 10,000 pounds, it is verified. You check the box.
Exactly, the math checks out. But validation asks an outward-facing, highly contextual question. Did we build the right thing for the intended stakeholder need?
Did we actually solve the human problem?
A product can pass every single verification test. It can compile flawlessly. But if the initial requirements were fundamentally wrong, if the bridge actually experiences 20,000 pounds of shear force from unprecedented wind loads in the field, the product fails validation. It is perfectly verified and completely catastrophically useless.
This reminds me of how tech companies approach prototyping. The mantra is fail fast, build a prototype, test it in the real world, but the sources warn that prototypes are incredibly dangerous if they aren't constrained.
A prototype is not a magic crystal ball. According to rigorous design methods, a prototype is an instrument built to answer one specific, explicitly stated uncertainty. What exact question are you asking the physical world?
So you have to isolate the variables.
Completely. If you build a looks-like prototype out of 3D printed plastic just to test the ergonomics and how it feels in a user's hand, you absolutely cannot generalize its structural performance. You cannot drop it off a roof and use that data to prove the final aluminum product will survive an impact. The prototype's fidelity must match the exact uncertainty you are targeting, or you are simply generating false data to validate your own biases.
You are lying to yourself with your own spreadsheets. Speaking of trying to force reality to behave, let's look at control theory. We mentioned dynamical systems earlier, the pencil balancing on its tip. When a system is unstable, the universal engineering instinct is to apply negative feedback. We see it in electronics, we see it in biology. Sweating cools you down, negative feedback stabilizes chaos, right?
This is one of the most persistent and dangerous myths in systems engineering. Our control theory sources issue a brutal correction on this. Negative feedback does not automatically stabilize an unstable open-loop plant.
But the very definition of negative feedback is that it pushes back against the error. If the drone tilts right, negative feedback tells the propellers to push left. How can that not stabilize it?
Because stability is not just about the direction of the push. It is entirely dependent on the loop dynamics, specifically the gain and the phase lag. Gain is how hard you push. Phase lag is how late you push.
Okay, I need a physical analogy. It's like driving on an icy road.
Exactly. The car starts to skid to the right. That is your error. Negative feedback dictates you steer left to correct it. But human reflexes have a phase lag. By the time you realize you are skidding and your arms physically turn the wheel, a fraction of a second has passed.
And because I'm panicked, I use a massive loop gain. I crank the wheel as hard as I can.
And what happens? You overcorrect. The massive gain combined with the phase lag means your corrective push arrives after the car's dynamics have already shifted. Your negative feedback actively drives the car into a violent skid in the opposite direction. You induce an oscillation. This happens in aviation all the time, known as pilot-induced oscillations, where the pilot's delayed, aggressive corrections actually tear the aircraft apart. The minus sign in your feedback equation is not a magical guarantee of stability.
The timing is just as mathematically critical as the force, but what if we rely on a black box mathematical model to predict the control system? The sources bring up transfer functions. These are equations that map the inputs to the outputs so we can see how the drone responds.
Transfer functions are incredibly useful, but they have a massive foundational guardrail. By definition, a transfer function mathematically assumes all initial conditions are zero. It assumes the system starts in a state of perfect absolute rest.
Which real life never does. What danger does that assumption hide?
It can hide catastrophic internal instability through a mathematical quirk called pole zero cancellation. Imagine a system with multiple internal components. One component is wildly unstable, growing exponentially, but another component mathematically cancels out that specific growth frequency.
So they mask each other.
From the outside, looking only at the input and the output through the lens of a transfer function, the system looks beautifully stable. The transfer function is a clean, simple curve. But inside the black box, that unobservable, uncontrollable, unstable mode is redlining. If you don't use a full state space representation to mathematically look inside the box, that hidden instability will physically vibrate the system to pieces while your monitors tell you everything is fine.
You cannot manage what you refuse to observe. Let's move from controlling physics to optimization, linear and integer programming. This is the math that logistics companies use to route delivery trucks, airlines use to schedule crews, and factories use to pack boxes. The goal is to find the absolute mathematically optimal solution.
And this relies on powerful algorithmic engines, primarily the simplex method for continuous linear programming and branch and bound techniques for integer programming.
Let's focus on integer programming because reality is discrete. I can't assign half a pilot to a flight or send 3.7 delivery trucks. The variables must be whole numbers, integers. The sources detail how the branch and bound algorithm searches for this optimal whole number. It builds a massive decision tree, branching out into thousands of possibilities. Here is a massive trap highlighted in the reading. If the algorithm is exploring a branch and it suddenly finds a perfectly valid integer solution, aren't we done? We found a workable schedule.
You found a solution, but you absolutely cannot claim you have found the optimal solution. Finding an integer solution at a non-root node of the search tree simply means you have established a new lower bound. It means you can look at that specific branch and say, okay, we have a workable solution here. Let's close or fathom this specific pathway because we know exactly what it's worth.
Like exploring a giant maze, finding a small piece of cheese down one corridor and blocking off the rest of that corridor because you've mapped it.
Exactly. But there might be hundreds of other active, unexplored branches in the tree. And one of those unmapped branches might contain a massive wheel of cheese, a vastly superior, vastly cheaper integer solution. The guardrail of branch and bound is that you cannot mathematically claim global optimality until every single active node in the entire tree has been fully evaluated or mathematically proven to be worse than your current best guess.
You have to prove the negative. You have to exhaustively prove that nothing else in the universe could possibly be better before you pop the champagne.
And to make that search faster, engineers often use a modeling trick called a big M formulation.
Right. Big M is a logical switch. It forces the math to turn a constraint on or off. Like, if variable y is 0, meaning we don't open the warehouse, add $1 million to the cost equation so the algorithm avoids it. You just use an arbitrarily huge number m to force the algorithm's hand.
And the warning in our optimization sources is severe. Using an arbitrarily huge m is a massive mathematical trap.
Why? 1 million is 1 million. It definitely turns the switch off.
Because it completely destroys the geometry of the LP relaxation. When the solver tries to figure out which branches of the tree to search first, it relaxes the strict integer rules and allows decimals, creating a geometric shape, a polytope that bounds the possible answers. If your m is 1 million, you have stretched that shape out into infinity.
Ah, so the algorithm has no idea where the edges are anymore.
The bounds become incredibly weak. The solver wanders aimlessly, exploring millions of useless branches because it can't mathematically distinguish the good paths from the bad ones. Furthermore, an arbitrarily large m induces the exact same floating point instability we discussed earlier. Adding 1 million to a tiny precise decimal variable causes catastrophic rounding errors. The solver might mathematically accept an invalid route purely because the floating point truncation buried the error. You must always derive the absolute smallest physically valid m based on the strict constraints of your specific problem.
So controlling machines, mitigating rounding errors, and keeping algorithms from searching infinity is hard enough. But the math gets exponentially more unstable when we try to optimize systems that involve human beings. People have agency. People lie, cheat, form cartels, and act in their own ruthless self-interest.
That is the ultimate complex system. And it brings us to the final phase of our deep dive, the human element, game theory and mechanism design.
Let's start with the most famous concept in economics, Nash equilibria. Thanks to Hollywood and movies like A Beautiful Mind, the cultural understanding of a Nash equilibrium is that it represents the globally optimal, perfect, harmonious outcome for everyone involved.
And that cultural understanding is a complete inversion of mathematical reality. A Nash equilibrium is not a utopia, it is simply a state of gridlock. The rigorous definition of a Nash equilibrium is a state where no single player can profit from a unilateral deviation.
Meaning, if everyone else freezes and stays exactly where they are, I have no mathematical incentive to change my strategy.
That is it. It says absolutely nothing about whether that gridlock state is good, fair, or efficient. Look at the classic prisoner's dilemma. Two criminals are interrogated separately. If they both stay silent, they get 1 year in jail. If they betray each other, they get 5 years.
And because they can't trust each other, the math dictates that the dominant strategy is for both to confess and betray the other.
Exactly. They both betray, and they both get 5 years. That outcome, mutual betrayal, is the unique Nash equilibrium of the game. It is the absolute worst collective outcome possible, highly inefficient and destructive. Yet it is mathematically stable because neither prisoner can improve their lot by unilaterally changing their mind while the other betrays them. There is nothing inherently optimal about a Nash equilibrium.
What about the minimax theorem? This is the idea that the best strategy is to minimize my maximum possible loss. Just play defensively.
Minimax logic is mathematically beautiful, but its absolute guardrail is that it only applies to two-player, strictly zero-sum games. If you win $1, I must lose exactly $1. In that highly constrained, purely adversarial environment, linear programming duality applies, and you can mathematically calculate the exact infallible value of the game.
But the real world isn't zero-sum.
Almost never. Most real-world interactions, trade, diplomacy, environmental treaties, are general-sum games. We can both get rich, or we can both launch nukes and lose everything. The moment you step into a general-sum environment, the defensive minimax logic completely breaks down. It will guide you into mathematically irrational decisions.
Let me push back on the inevitability of the prisoner's dilemma. I've read that if you just force the players to repeat the game over and over again, they eventually realize that mutual destruction is stupid and they learn to cooperate. Doesn't repetition solve the inefficiency? I've heard economists quote the Folk theorem to prove that repeating a game creates cooperation.
I have to shoot that down because it is a massive oversimplification that policymakers fall for constantly. The slogan, repetition creates equilibria, is not a standalone mathematical theorem. The actual, rigorous folk theorems require explicit, fragile hypotheses to function.
What kind of hypotheses? What are the guardrails for cooperation?
First, the players must be sufficiently patient. They have to mathematically value future rewards almost as highly as immediate payouts. This is measured by a discount factor. If a CEO is desperate for a quarterly bonus, their discount factor drops, and they will betray their partner for immediate cash, regardless of the long-term relationship.
Patience is mathematically required. What else?
Second, there must be suitable, perfect monitoring. I have to be able to accurately and instantly observe your past actions so I can mathematically punish or reward you. If your actions are hidden behind corporate secrecy, the threat of punishment vanishes and cooperation collapses. Third, any cooperative outcome must satisfy individual rationality. It must yield a higher payout than the absolute worst punishment the group can inflict. If those rigorous conditions aren't met, repeating the game 1,000,000 times will not magically guarantee cooperation.
It just means you get betrayed 1,000,000 times. It's all about the guardrails. Let's expand this from economics into biology and evolution, evolutionary game theory. We all heard survival of the fittest. Our sources spent a lot of time on something called an ESS, an evolutionarily stable strategy. Is an ESS just a biological translation of a Nash equilibrium?
It is fundamentally related, but it is mathematically much stronger, much more robust than a standard Nash equilibrium. An ESS is classically defined for symmetric games, where a large population of organisms is randomly interacting. For a strategy to be declared an ESS, it must not only be a Nash equilibrium, meaning it's stable when everyone plays it, but it must actively mathematically resist rare mutant invasions.
Mutant invasions, like an X-Men scenario.
In a genetic or behavioral sense, yes. Suppose a population of birds is perfectly balanced, all playing strategy A, which is a Nash equilibrium. Suddenly, a tiny fraction of the population mutates or migrates in and starts playing a completely different strategy B. For strategy A to be a true ESS, the incumbent birds playing A must achieve a strictly greater reproductive fitness in this new mixed population than the mutant birds playing B. The math must dictate that the population actively pushes the mutants back into extinction.
So it's not enough to just sit comfortably in a gridlock. The strategy has to have an immune system. It has to actively fight off perturbations.
Exactly. And this leads to another subtle cognitive trap in how we model these populations using differential equations called replicator dynamics. Biologists look for rest points in the math where the population percentages stop changing. But the guardrail here is that a mathematical rest point does not imply a stable Nash equilibrium.
How can a population be totally at rest, mathematically unchanging, but not be in equilibrium?
Because of the structure of standard replicator dynamics, the math inherently preserves zero population shares. If a specific strategy is completely extinct, if exactly 0% of the population possesses that gene, the mathematical growth rate for that gene is multiplied by 0. It cannot magically spontaneously generate.
So the math says the system is at rest.
Right. But it might be at a rest point simply because a highly aggressive, highly effective mutant strategy is artificially absent from the simulation.
It's like looking at a computer model of a medieval continent and declaring the population is perfectly stable against disease purely because you haven't mathematically introduced the Black Plague yet. The moment the boundary is crossed, the rest point violently collapses.
A boundary rest point is a mathematical illusion of stability. Okay, let's bring all of this together with the pinnacle of economic engineering. Mechanism design. This is where we don't just play the game, we design the rules of the game, like tax codes, voting systems, or billion-dollar spectrum auctions, to mathematically force self-interested liars to produce the outcome we want.
It's reverse game theory, and the holy grail of mechanism design is the revelation principle.
Yes, the revelation principle is a beautiful, sweeping analytical tool. It mathematically proves that if any desired outcome can be implemented by some convoluted, complex set of rules, it can also be implemented by a truthful, direct mechanism.
A truthful mechanism, meaning we can always design a game where honesty is mathematically the best policy for every single player. That sounds like a utopian silver bullet.
And treating it like a silver bullet is a massive engineering failure. The revelation principle is an analytical reduction theorem. It is a mathematical proof that a truthful mapping theoretically exists. However, and this is a multi-billion-dollar guardrail, the principle does not guarantee that this truthful mechanism is computationally feasible to run.
Right. Going back to NP hardness, the truthful mechanism might take a supercomputer 1,000 years to calculate.
Exactly. It also does not mean the rules are simple enough to actually communicate to human bugs. And most critically, the revelation principle assumes isolated players. It absolutely does not guarantee that the mechanism is immune to players forming cartels, colluding with each other, or creating fake bidding identities to game the math.
Can we look at a real-world example of this? Let's look at the famous Vickery auction, also known as the second price auction. This is widely used in online advertising. Everyone submits a sealed bid. The highest bidder wins the item, but the genius is that they only pay the price submitted by the second highest bidder.
Right. And the beautiful theoretical result, which won a Nobel Prize, is that in a Vickery auction, truthful bidding is always a weakly dominant strategy. The math proves that trying to game the system by bidding lower or higher than your true valuation will only ever hurt you. You should always just bid exactly what the item is worth to you.
So the mechanism works. Truthful bidding is mathematically guaranteed to be optimal.
The math is guaranteed, but only under incredibly strict, fragile guardrails.
Yeah.
Standard private value and quasi-linear utility settings.
Okay, unpack those constraints for me.
Private value means my internal valuation of the item does not depend in any way on your valuation. I am buying a painting for my living room because I like it. Quasi-linear means I value money in a perfectly linear, unbounded way.
But the real world is really that clean.
Almost never. What happens when you introduce budget constraints? What if I genuinely value the painting at $1 million, but I only have $10,000 in my bank account? The quasi-linear math breaks. Or, what if we were in a common value auction? We are oil companies bidding on the drilling rights to attractive land. The oil under the ground has one true, common value, but neither of us knows exactly what it is.
So my estimate of the value absolutely changes if I find out that you think it's worthless.
Exactly. If you bid incredibly high, it signals to me that your geological surveys found massive reserves, which mathematically forces me to update my own valuation. The moment you introduce budget constraints, risk aversion, or common values, the theoretical guarantee of the Vickery auction violently shatters. Truth-telling is no longer a dominant strategy. Bidders resort to complex, defensive shading, and the supposedly perfect rules of the auction break down in the real world. We saw this in the early telecom spectrum auctions, where flawed mechanism designs allowed telecom giants to signal each other through the bids and collude to buy billions of dollars of public assets for pennies.
Because the designers trusted the formula but ignored the guardrails. This has been an absolutely mind-bending deep dive. From F equals ma requiring constant mass and non-rotating frames, to matrices requiring factorization instead of inversion, to the central limit theorem ignoring fat tails, to Nash equilibria being a trap of gridlocked inefficiency. The overarching, undeniable lesson here is that formulas and theorems are only as good as the physical and mathematical boundaries that cast their shadows.
Precisely. The assumptions we gloss over, the constant mass, the infinite precision, the independent events, the zero-sum constraints, those are the invisible scaffolding of reality. Ignoring those underlying assumptions isn't just a rounding error. It is the fundamental root of catastrophic failures in aerospace, in algorithmic design, and in global economics.
Before we sign off, I want to leave you, the listener, with one final, deeply provocative thought. We've spent this entire hour tearing down the guardrails of deterministic classical math and physics. But what happens when you scale down and hit the ultimate physical boundary of the universe? I'm talking about quantum mechanics.
If you think classical intuition is fragile, quantum mechanics shatters the very concept of certainty entirely. In standard quantum mechanics, we cannot just pinpoint a particle's location. We deal with quantum states. And a massive mathematical guardrail here involves how we define what we actually know about a system using something called a density operator, denoted by the Greek letter rho.
How does a density operator differ from classical probability?
In classical probability, if you don't know if a coin is heads or tails, it's just statistical ignorance. The coin has a definite state, you just haven't looked yet. But in quantum mechanics, we differentiate between pure states and mixed states. A pure state is a system where we have maximal perfect knowledge. It might be in a quantum superposition, like being both heads and tails simultaneously, but mathematically, we know exactly what that superposition is. For a pure state, the mathematical trace of the density operator squared, the trace of rho squared, is exactly equal to 1.
It represents perfect, mathematically complete quantum information.
But the universe is rarely pure. Most systems interact with their environment. They become entangled. When a quantum system is open to the environment, or when we are only looking at a subsystem of a larger entangled reality, we have to use a mixed state. It is a statistical mixture of different quantum superpositions.
The ultimate messy reality.
And here is the mathematical boundary. For a mixed state, the trace of rho squared is strictly, fundamentally less than 1.
Less than 1, meaning that even if you measure everything it is physically possible to measure about that local system, the math itself dictates that information is missing.
Exactly. The information isn't just hidden, it is non-local. It is smeared across the entanglement with the environment. There is a fundamental, inescapable limit to certainty built into the very algebraic structure of the universe.
It leaves you to ponder. If our deterministic macroscopic math, our forces, our matrices, our auctions, is already so fragile, so full of caveats and hidden assumptions, how do we begin to confidently model a universe where uncertainty and missing information are woven into the very density of reality itself? The next time you see a clean, elegant formula promising you a perfect answer, I encourage you to look closely at the edges. Look for the hidden assumptions in your own work, in the code you write, and the models you trust. Thank you for joining us on this deep dive.